Hello everyone. Today I am going to present the paper Magnet Towards Adaptive GUI Agents with Memory-Driven Knowledge Evolution. So basically this paper is about mobile GUI agents, which are the AI systems that can use phone applications by looking at the screen and taking some actions. The main problem is that these agents often fail when applications change after the update. So here Magnet tries to solve this problem using memory. So why do these agents often fail after app updates? So the author explains the two major reasons, which are the appearance drift, which means the icons, buttons, and screen looks different after the update. The second reason is workflow drift, which means the steps to complete the same task may change. But the two things which usually stay stable are the meaning of the interface and the goal of the user. So even if the screen changes, the real task is often still the same. What does this task, like the task does the paper solve? This paper studies like mobile task automation. So basically a GUI agent gets three inputs, which is the user instruction, the current screenshot, and the action history. Then it tries to predict the next action, such as whether to tap, type, or scroll. Its goal is to complete multi-step tasks automatically. For example, it may search for Google stock price or let's say change the currency settings to US dollars. And yeah, moving on to the architecture of this entire research paper. So the workflow goes like first, the human tries to give a natural language request. Then this request goes to the planner, which breaks the task into smaller subtasks. And then after that, the actor performs some actions inside the mobile application and which goes on to the environment, which is basically the phone screen where the changes after every action can be seen, and it also gives new feedback. So this loop continues until the task is finished. In Magnet, basically, the planner uses procedural memory and the actor uses stationary memory. So basically the main idea of Magnet is the same, which is this framework has two memories. The first is the procedural memory, which remembers the workflows, the steps of a task, and the second is stationary memory, which remembers the meaning of the UI elements like the buttons and icons. Then the magnet keeps updating both memories over time. So basically moving on to the procedural memory, which is the workflow memory. So it stores the general steps of tasks from successful examples, also helps the planner break a big task into smaller tasks. It is also useful when the app layout changes, but the task goal stays the same. For example, a search task may still follow the same flow, which is like open the application, tap search, type the query, and choose the result, even if the interface looks different. So the stationary memory, it also stores two things together, which is what a UI element does and what it looks like. This helps the actor find the correct button or icon even when the appearance changes. The paper also builds a dataset called the UI40K for this purpose. So basically the main idea here is that the agent remembers the function of a button, not just one old picture of it. How the magnet keeps learning. So we can see that there is another important part in this research paper, which is a dynamic memory evolution. Basically, magnet does not keep the memory fixed. After each successful task, it updates memory by adding new workflows and new UI examples. More useful and more recent memories are given high priority. Older or less useful memories move lower with the priorities. So basically, the agent keeps improving from the past experiences instead of staying static. How is this magnet evaluated? Basically, the authors test the magnet in both offline and online settings. The offline benchmarks are AITZ, GUI, Odyssey, and Amex. They also test shifted the settings, such as template shifted, app shifted, and domain shifted to see whether the agent can still perform well when things change. For offline evaluation, they use success rate and grounding accuracy, and for the online evaluation in Android world, they use the full task completion rate. So this magnet is compared against some baselines. So basically to improve, like to understand the performance of magnet, these are the baselines which it gets compared with. So some are the specialized trained models which we can see over here. we compare with these scores, and then it also tries to compare with the training free baselines or training free agents. And also importantly, it compares along with the online baselines as well. So basically, which instead of fully retraining, the important point in this magnet is that the magnet mainly adds memory on top of an existing model instead of fully retraining the whole system. So here you can see the visualizations of the offline results. So basically, you can see that Magnet is consistently performing better than the main free training free baselines. For example, on AITZ, so you can see that the code is 41.09 and the Magnet's success rate is like 43.50. And same goes with the GUI Odyssey as well as the Amex. You can see the difference of increase in the success rate. And yeah, so the main takeaway from this is that the magnet is very strong, practical, as well as competitive. And at the same time, this paper also notes that some specialized trained models can still have higher absolute scores. Basically, moving on to the online results in Android world. So we also compared this thing here as well. You can see that the magnet is performing pretty well compared to the other agents. So it gives you the success rate as 42.6% in the online comparison as well. So how does this magnet improve over time? Basically, it starts with some initial memory from the Amex dataset and keeps updating memory after each iteration. The performance rises from 31.1 at the beginning to 37.7 after the first iteration, then 39.3 after the second, and finally 41% after the third iteration. This shows that the magnet can continuously learn from successful past experiences and adapt better over time. So basically, very, very good at generalization. And why does this magnet always work? So basically, when the author compared everything, he said that when we use stationary memory, the improvement is very small. When we use procedural memory, the improvement is larger. But when we use the both the memories, the results are always the best. You can see here as well that on Amex and on GUI Odyssey, the success rate is rising from the baseline, which is 59.68 for Amex, to 62.34 and 48.13 for GUI to 49, like 50.16 when we use Magnet. Moving on to the challenges and error cases. So this paper gives three examples. Basically, one example says that a baseline agent clicks the wrong tab and while trying to search Google stock, but procedural memory helps Magnet follow the correct workflow. In the another example, you can see that the baseline confuses the Tumblr icon with threads, but stationary memory helps retrieve the correct icon. Similarly, in the Subaru navigation example, you can see that both memories are needed together to plan correctly and act on the right interface. These cases show the real challenges, which is like application drift, sorry, the appearance drift, workflow drift, and similar looking icons, as well as changing app environments. Final takeaway from this entire research paper and my presentation is like basically to conclude, I'd say Magnet helps GUI agents adapt by remembering two majorly important things, which is what UI elements mean and how tasks are usually done. Its main strengths are better adaptation, better generalization, better online performance, and continual memory updates. At the same time, it also has some limitations, so it needs successful past experiences to build memory and give better results. It may struggle in completely new domains, and workflow clustering can be difficult when tasks are very diverse. So overall, I'd like to say the paper shows that stable meaning and stable intent are more useful than memorizing old screens. Thank you.